Welcome back. So we'll continue the discussion on this integration by parts. As noted earlier, so if you want to establish this integration by parts for functions in H1 omega, we need to define the values of this H1 functions on the boundary, and which we call it trace. Okay, so that's the first task, and then we use the density. Okay, so let me quickly complete that density result. So let me just, so this is density result. So this we have already seen earlier. So how the extension theorem helps us in getting this result. Okay, so suppose, so omega is a bounded domain. Suppose, so I'll just write the condition on the boundary is of class CM. Then CM omega bar is dense in HM omega. Okay, so again, so let me just write that. So that is given F in HM omega, there is phi, or you can write in terms of sequence. Okay, let me just write sequence. Omega bar such that F minus phi L in H1 norm, HM norm tends to 0 as, of course, the same statement you can write in terms of given any epsilon, you can find a smooth function approximating the HM norm. So some time back, just recall this, if we restrict to any compact search, so this recall, and at that time I commented extension to the whole domain is quite technical, and that's what we have developed now. So if omega tilde is open in omega, and omega tilde bar is also in omega, then this, then F epsilon minus F H1 omega tilde. So if you restrict to any compact subset of omega, then this tends to 0 as epsilon tends to. Okay, so now we want to replace this omega tilde by, so this is modifiers of F, and we know they are in C1 C infinity. So in particular CM, modifiers of F. So this is in H1 0 omega, HM omega. Okay. that. Okay, so now we just quick proof, already developed all the tools. So just proof. So suppose omega tilde is contains omega such that omega bar is compact in omega tilde. So you can cover by cube or parallelepiped, okay, anything. Okay. So by extension theorem, there exists an f in omega tilde which is an extension of f given f. So from the previous note we observe that this then f epsilon minus f hm I'll put k here tends to 0 as epsilon tends to 0 for any compact k in omega tilde. Okay. In omega tilde. So in particular we can use it for, so in particular this f epsilon minus f, we can take omega. Okay. So this tends to 0 as epsilon tends to 0. But this f is an extension of our given f, so this f epsilon minus f. Okay. And f epsilons are smooth. So f epsilon, in fact they are all C infinity functions. Okay. So that in particular they are CM functions. So once we have the extension result, so density result easily follows. So just observe this. Okay. So we really do not, we have some relation with this f, but when you take these modifiers it's really mixed up. Okay. So this you cannot really, so you are extending f to a larger domain and then you are really mixing. Okay. So this but yet you are close to f in this hm norm. So this is an interesting element, this f epsilon. Okay. We have knowledge of this big f, but when you take the modifiers, so they are really mixed up. Okay. So in fact you can also use this extension theorem to extend the function to whole of Rn. So if time permits I will say that thing. So once you extend to whole of Rn, you can use the powerful tools like Fourier transform and other things very easily to derive many things, as long as you have, see on the extension we want to have control, that is important. Okay. So that is it is not just an arbitrary extension, we have the full control on that extension. Okay. So with this thing now we will move on to this topic. So this is a delicate topic, trace of an H1 function. So, let us start with an H1 function. So, here is our omega. So, in fact, we can take any surface here and try to give values of the given function on this S. Okay. So, del omega, so we assume that is in C1. Okay. So, let me write okay, u is in H1 omega. Okay. So, these are just L2 functions and whose distribution derivatives are also in L2. So, as such, since they are defined only almost everywhere on a set of measure 0, we cannot really assign any value, and if S is a n dimensional C1 surface, for the time being that is sufficient. On the other hand, if u is continuous function or u is a function defined at every point, then obviously we can talk of what this u restricted to S. Okay. But in general, if we have just an H1 function, this does not make any sense, does not make sense almost everywhere. Okay, that is because this S has n dimensional measure 0. Okay. So, our task is to make sense out of this, okay, and also some integrability condition of u on the surface S. Okay. So, that is our aim here. Okay. So, let us begin with first easier part, and you also see how these techniques of approximation by smooth function help us at every stage. Every stage we are doing that thing. Okay. So, let u belongs to C1 with compact support. Okay. And so, I want to take another piece. So, let S be a simple piece. So, given by, again for the sake of easy writing, so I use this coordinate p of x prime. So, x prime is and these vary in a domain D. This is projection of S onto x n equal to 0, and our phi, since we are assuming C1, so this C1 C1 d bar. Okay. And okay, since omega is bounded, so this is another omega is bounded. So, let omega sit in a cube. Okay. So, this x 0 x for some a positive. This positiveness you see in a minute why you are doing that. Of course, we can always translate omega to achieve that. It is also for ease of writing. Okay. So, that means for example, this phi is positive. Okay. So, since omega sits here, so this S also sits there, so phi is positive. Okay. So, now this what did I use? I have used U. Okay. So, U restricted to S means U x prime phi x prime, because the action coordinate is given by phi x prime, and that by using one dimensional calculus we write it 0 to phi x prime del u by del j n x prime j n d j n. See that assumption that omega is otherwise I have to worry about the sign of phi x prime, whether it is less than 0 or bigger than 0. So, accordingly I have to put that thing. So, now we have assumed that thing. So, that is no problem at all. So, you can, even if it is otherwise, you can always do that. So, this helps us. So, I do not have to worry about that. Okay. So, that implies u restricted to S square is less than or equal to. So, u is Quasi-Schwarz. So, you get A 0 to A. So, because that is also less than or equal to A. So, del u by no, maybe I should next step I will do that. Okay, it does not matter. Okay. So, now multiply both sides. In order to get the surface measure, both the sides by that factor. So, 1 plus grad phi square and integrate over d. So, d the projection of S onto the. So, by definition, so the left hand side will be, so u of L2 S square is less than or equal to. Now, I just let me write everything a constant. So, this is u of H1 omega square. Okay. So, starting with a C1 function having compact support. So, let I stress that. Okay. So, starting with a C1 function with compact support and taking S to be a simple piece. Okay. So, we derived this estimate on the L2 norm on the surface S. Okay. So, this readily extends, okay, that is next observation, this inequality readily extends to so we have taken C1 function with compact support, okay, extends to u in C1 omega bar. Why is that? So, if u is in C1 omega bar, okay, extend u to some omega tilde containing omega bar, okay, and use also again C1 with compact support on omega tilde. So, this is by the extension theorem, and now you apply this inequality for this extension, but extension norms are controlled in terms of the original function. So, that is why they are important. They are important. So, though you get here for the extension function, but the norm of the extended function is estimated in terms of the original function. So, that is why they are important. So, this inequality now valid for all u in C1 omega bar. Okay. Okay. So, so this holds for only simple piece. Okay. So, let us not be in a hurry. So, now take S to be any C1 surface, because since we are considering surfaces which are only finite union of simple pieces. Okay. So, we have derived this for only simple piece, but now you join together. So, that is valid for any C1 surface. Okay. So, I forgot to tell that, because this is only for one simple piece, but then you use the definition for finite union and you get that. Okay. So, now let u be in H1 omega. So, by the density result, so there is a sequence UL in C1 omega bar. See, for extension we do need smoothness on the boundary, so that is why we assume that. Okay. So, this boundary smoothness is always, otherwise we cannot get that extension result, okay, such that UL minus U in H1 omega tends to 0. And since these are C1 omega bar functions, so we can apply this inequality, okay, which is derived for C1 omega bar functions, but okay, so let me write that UL minus UK L2S is less than or equal to UL minus UK H1 omega. Okay. So, this is because ULs are all in C1 omega bar, but UL converges to U in H1 omega. So, in particular that is a Cauchy sequence. So, this goes to 0 as LK tends to infinity. Okay. So, therefore, this thus UL converges to, so let me, since I am using that one, so for the time being UL converges to U in L2S. So, that gives us this existence of this function U. Okay. So, we call u as the trace of u. Of course, this to call this qualification requires one more argument. So, here what if I take another sequence which converges to u in H1 norm. Okay. So, easy to check, that u does not depend on the sequence UL. So, that means if you take another sequence, so finally this one will be the same. So, that requires some 2-3 steps, but this is very routine thing. Okay. So, in this way so we have defined a function defined on the okay. So, this is on any surface. So, in particular trace of u on S. Okay. So, that is on S this. So, in particular, so in fact yeah, in particular if we take S equal to del omega, we obtain the trace of any H1 function on del omega. In fact, usually if you see the literature, so trace is referred to only that function defined on the boundary. Okay. So, we observe the following. Okay, that is okay. So, for any u in H1 omega, so we have the notion of trace of u. Okay. So, for the time being I am just temporary notation, usually we will not write that. Okay, that we just write u only, denoted by trace of u on del omega such that trace of u belongs to L to S. So, if you observe the above this arguments what we did here. Okay. So, given u in H1 omega, so there exists a sequence UL in C1 omega bar such that UL minus U in H1 norm tends to 0, and also, so this is also important, and also UL being C1 functions, they have the values on the boundary are well defined, so there is no problem there. So, we also have this L2S tends to 0 as L tends to infinity, because this is also important. So earlier we have got only this one, and now with introduction of this new notion trace of u on the boundary. Okay. Now we are using that del omega. That's important. Okay. So with this thing, so let me first this integration by parts formula. So if uv are in h1 omega, so where the boundary of omega is class C1, class C1, then omega u dv by dxi del omega uv nu I. So I will explain what that nu I is. So this is the surface measure on del omega minus omega v. So this is for I is equal to 1 to n. And now using this integration of parts formula and some manipulation, you can derive divergence theorem, and with more assumption on u and v you can derive Green's formula, all those things. So there is absolutely no problem. So now this u and v, see already we started writing. So these are traces of u and v respectively. Okay, so this is immediate now. Okay, so the proof. So nu I, so nu is equal to nu 1 nu n is the outward unit normal to the boundary. So here is the boundary. So boundary point x. So this is new. Okay, so it changes. Okay, so this C1 assumption, this is well defined. So it's continuous in fact. So this u and v are traces of u and v. So they are in L2 over the boundary, and this is continuous. So this surface integral is finite, and since both u and v are in H1, so this is product of two L2 functions, that is also product of two L2 functions. So everything is fine. Okay, so this proof is just one line. So approximate u and v by C1 omega bar functions and pass to the limit. Okay, that's just one line. Okay, so this going to be used very often in the second part of this course. So this is an important. So you understand the notion of the trace and this integration by parts very well. Okay, so I stop here and will continue next time. Thank you.